In this video, we'll be talking about surds. Now let's first understand what exactly surds are. Now let's consider two sets of radical numbers such as these. And this is the first set. All these are numbers that are expressed under the radical sign of the square root. Now, let's consider their solutions as well. Now we would find that the solutions of this first set of numbers are totally different from this set of numbers. Now we have the square root of 4 to be 2, the square root of 49 to be 7, the square root of 81 to be 9, and the square root of 144 to be 12. Now these set of solutions are rational numbers. But you would find that if we go to this right side, the sets of numbers on the right side, the square root of 2 happens to be, if you evaluate this with your calculator, is 1.41421,356 continuing. It's a continuous number that doesn't have an end, and the more digits, the number of digits you actually get is dependent on how much numbers your calculator can handle. It's the same for the square root of 5, the square root of 11, and the square root of 23. Now, these numbers that continue, such as these, are called irrational numbers. Now they're called irrational numbers. They're called irrational numbers because they cannot be expressed as a ratio. Now you would remember that when we had spoken about ratios and fractions, we had said ratios are also another form of expressing fractions. Now these numbers on the other hand can be expressed as fraction. We know that if we say 8 divided by 4, for example, this is going to be 2. And so this is a fraction that represents 2. This is the same thing as this. They are just being expressed in different ways. However, these numbers cannot be expressed as a fraction such as this. And that's why they are called irrational. We cannot be expressed as a ratio. And so for radical numbers that have rational solutions, for radical numbers, and by the way, this sign which we use in representing the square root is called a radical sign. And so for radical numbers such as the square root of 4 that have rational solutions such as 2, such as 7, such as 9, definite rational solutions, these are not surds. These are not surds. Now, these radical numbers which have irrational solutions, which means numbers that seem to be continuing, square root of 11, 3.31662 continuing, square root of 23, all these numbers, these are the ones that are called surds. And what that means is if you're solving a mathematical problem and you get to the point where you have the square root of any of these numbers, by the way, these numbers that have rational solutions to their square roots are called perfect squares. So 4 is a perfect square, the square root is 2. 49 is a perfect square, the square root is 7. 81 is a perfect square, the square root is 9. 11 is not a perfect square because we don't have a rational solution for it. Now, if you're solving a mathematical problem and you get your solution as the square root of 81, for example, now it's mathematically correct that you express your solution definitely as 9. And if you have square root of 144, you have to express your answer as 12 because that is the natural solution. Now, but for square root of 23, in most cases, you don't have to go further and write it out in decimal places. But if you leave it as the square root of 23, it is not mathematically wrong. And that is why we are interested in surds. Now, just to be sure that we understand, let's look at certain numbers and tell if they are surds or not. Now, if we look at these numbers that we have here, which of these are surds and which aren't surds? Now, the solutions to these are, and we can see that the square root of 36 is a rational number, so this is not a surd. Now, the square root of 121 is 11, a rational number, so this is no surd as well. Now, the square root of 15 is equal to this irrational number 3.892 blah blah blah, and that means that this is a surd. Now the square root of 9 is 3, not a surd. The square root of 3 is 1.720, so this is definitely a surd. Square root of 6, that's a surd. Square root of 100 is 10. This is a rational number. It can be expressed as a fraction. So this is not a surd. And as you might have guessed by now, the square root of 200 is definitely a surd, because it is an irrational number 14.14213 continuing. Now that we can identify surds, let's look at the basic properties of surds. Now we're going to be looking at three properties, and the first one is that it states that if we have the square root of a, b, that this is equal to the square root of a multiplied by the square root of b independently. Now, if you remember the laws of indices say that a b raised to the power n is equal to a raised to the power n b raised to the power n. This was one of the things that we learned when we looked at indices and the laws of indices. And so if we apply that to this here, we know that if you say the square root of a, this is the same as saying a raised to the power half. So definitely the square root of ab is equal to a b raised to the power half. Now if we apply this law, we can say that this is equal to a raised to the power half multiplied by b raised to the power half. And this is exactly what we're saying here, because this is equal to the square root of a multiplied by the square root of b. So that's proof that. But if we actually look at real numbers in expressing this, if we have that the square root of 16 multiplied by 4, and we're trying to prove that this is equal to the square root of 16 independently multiplied by the square root of 4. Now let's solve this side first. We have that 16 times 4 is equal to the square root of 64. And we know that the square root of 64 is a rational number 8. Now what about the square root of 16 independently? That is 4. And the square root of 4 is equal to 2. So 4 multiplied by 2 is equal to 8. So this is equal to this. So you can tell that when you have the radical sign over a multiplication, this is the same as the square root of the constituents under the radical sign multiplied independently. So the square root of ab is equal to the square root of a multiplied by the square root of b. Now the second property we'll be looking at is a little bit similar to the first one, but this is division. And we're saying that if we have the square root of a divided by b, this is equal to the square root of a divided by the square root of b. Now we're going to be proving this using the law of indices as well, that says that a over b all raised to the power n is equal to a raised to the power n over b raised to the power n. So if we apply that here, we have that a over b raised to the power half, and that goes without saying that this is equal to a raised to the power half over b raised to the power half, and this is equal to the square root of a over the square root of b. Now if we use another example, or the same example, or the same numbers like we had used in the previous example, which is if we have the square root of 16 over 4, and we're trying to prove that this is equal to the square root of 16 over the square root of 4. So let's do this. Now 16 divided by 4 is equal to 4. So we have that this is equal to the square root of 4, and the square root of 4 is equal to 2. Now what about this? The square root of 16 we know is 4, and the square root of 4 is equal to 2. Now 4 divided by 2 is equal to 2. So we can see that the square root of a divided by b is the same as the square root of a divided by the square root of b. So the third property we'll be looking at says that if you have a number a, the square root of a number a, and you multiply it by itself, the square root of a as well, this is the same as saying that the square root of a squared, and this is going to give you a. So if you multiply the square root of a by itself, or you square the square root of a, you get a as well. And this is the same as saying that we can branch out by saying that if you have a squared and you look for the square root of a, you would also get a. Now, the square root and square are inverse operations, which means they cancel out each other. So if you square a number and then you look for the square root of that number, you get the number back here. So if we try this out, we say, for example, the square root of 9 multiplied by the square root of 9. Now this is equal to the square root of 9 is 3 multiplied by the square root of 9 second one, which is 3, and we have 9. So the square root of a multiplied by the square root of a is equal to a as well. And those are the three properties. If we do a quick summary of those three properties, now the first one says that if you have the square root of a, b, this is the same as the square root of a minus the square root of b. The second one says if you have the square root of a over b, this is the same as the square root of a over the square root of b. And the third one says that if you have the square root of a squared, this is the same as a squared, the square root of a squared, and this is equal to a. Now, the only thing I have to remind you of here is that we can go both ways. You can go this way, that split up this, or you can combine this to give you this as well. So let's move up to simplifying surds. If we have a radical expression such as the square root of 45, now the aim of simplifying this expression is so that we write down this surd in the simplest indivisible surd possible. And to do that, the method I would advise that you do is write out or think about the factors of 45. Now the factors of 45 are 1, 3, 5, 9, 15. Now I would say that you look for the highest perfect square number that you have here. Now 1 is not 3 is not a perfect square, 5 is not a perfect square, 9 is a perfect square. So we take note of that. 9 is a perfect square. But do we have any perfect square greater than 9? 15 is not a perfect square, and we can't use 45 because that's what we're trying to break down. So 9 is a perfect square. So this is equal to the square root of 9 multiplied by, what do we have to multiply by 9 to get 45? And that's 5. So 9 multiplied by 5. Now don't forget that this is the same as this. Remember what we just said, that if you have the square root of ab, this is the same as the square root of a multiplied by the square root of b. Now it means that we can rewrite this as, let me go back to my black pen. We can rewrite this as the square root of 9 multiplied by the square root of 5. And we know that the square root of 9 is equal to 3 multiplied by the square root of 5. So this expression is equal to 3, 5. And this is the simplest surd that can be derived from the square root of 45. Now the reason we need to do this, we will see later when we try additions and subtractions of surds, because there are bigger numbers that we need to reduce to its lowest term so that addition and subtraction of surds are easier for us. Now let's take on other examples so that we understand this better. If we're asked to simplify the square root of 32, so we do the same thing. We think about the factors of 32, which are 1, 2, 4, 8, 16, and 32. Now we look for the largest perfect square that we have. Now 2 is not a perfect square, 4 is a perfect square, but let's see if we have something larger. Now 8 is not a perfect square, but 16 is a perfect square. So we are not going to be using 4, we're going to be using 16. Now what number must we multiply? Oh, first let's write that down. So that's going to be equal to, this is going to be equal to the square root of 16. Now what number do we have to multiply by 16 to get 32? And that's 2. So this is the same as the square root of 16 multiplied by the square root of 2. And we know that the square root of 16 is 4 multiplied by the square root of 2. So this is equal to 4 root 2. And this is the simplest surd we can get from the square root of 32. Now what if we look at the square root of 75? Now what are the factors of 75? Factors of 75 are 1, 3, 5, 15, 25, and 75. So what's the largest perfect square we have here? That's 25. 25 is the largest perfect square. And by perfect square, I mean numbers that have rational answers to the square root. 25, the square root of 25 is 5. Easy. 15 is not a perfect square because the square root of 15 does not give you any rational number. The square root of 5, no rational number. Now, 25 is the largest perfect square that we have here. So this is going to be equal to the square root of 25 multiplied by, now we have to multiply 25 by 3 to get 75. So that's this. And this is equal to the square root of 25 multiplied by the square root of 3. This is equal to, the square root of 25 is 5. And the answer to this sum is 5 root 3. So the factors of 99 are 1, 3, 9, 11, 33, and 99. Now the largest perfect square we have here, 33 is not a perfect square, 11 is not, 9 is the largest perfect square. So we can rewrite this as equals 9 multiplied by, we have to multiply 9 by 11 to get 99. So 9 multiplied by 11 is equal to 99. And we know that this is equal to the square root of 9 multiplied by the square root of 11. So this is equal to, square root of 9 is 3 multiplied by the square root of 11. So our final answer can be written as the square root of 3 root 11. And that is the simplest surd we can get from that. Now to this. Factors of 108 include 1, 2, 3, 4, 6, 9, 12, 18, it's quite a lot, 27, 36, 54, and 108. So let's look for the largest perfect square we have here. Okay, so we can start from the right side just so that the last one we get. 108 is not a perfect square, so no. 54 is not a perfect square, but 36 is a perfect square. And that's the largest perfect square we have here. So we can rewrite this as equals the square root of 36 multiplied by, what do we have to multiply by 36 to get 108? And that's 3. So this is also equal to the square root of 36 multiplied by the square root of 3. Now, the square root of 36 is equal to 6 multiplied by the square root of 3. And so our final answer is 6 root 3. So if we have this example 8 root 20 and 5 root 80, and we are requested to simplify this. Now we can break this down, or let's write down the factors of 20 like we would. 1, 2, we know that 4 is a factor of 20, we know 5 is a factor of 20, 10, and 20. Now the largest perfect square we have here is 4. So we can rewrite this expression as 8 multiplied by the square root of 4. Now this 8 comes down here. Now we break this 20 down into 4 multiplied by 5. So we can rewrite this as 8 multiplied by the square root of 4 multiplied by the square root of 5. Now we know that the square root of 4 is 2, so this becomes 8 multiplied by 2 multiplied by the square root of 5. So we can go ahead and multiply these two. 8 times 2 is 16. And then we have root 5 there. So that is the final answer. Now to the next one. The factors of 80 include 1, 2, 4, 5, 10, 16, 20, 40, and 80. Now what's the largest perfect square we have here? Let's start from the largest number. 80 isn't a perfect square, and even if it is, we can't use it. Now 40 is not a perfect square. 20 is not a perfect square. 16 is a perfect square. So that's the number we'll be using. So we can rewrite this as 5 multiplied by, we break this 80 down into 16. Now we have to multiply 16 by 5 to get 80. So that's that. And so this can be written as 5 multiplied by the square root of 16. So we're breaking this down into the square root of 16 multiplied by the square root of 5. This is equal to 5. We know that the square root of 16 is equal to 4. So 5 times 4 multiplied by the square root of 5. So 5 times 4 is equal to 20 multiplied by the square root of 5. So 20 root 5. That's the simplest surd we can get from this expression. So that's how we simplify surds. Now what we've done in this case is we've gone from like our first example where we had the square root of 45 and we wrote this as 3 root 5. Now it's possible that we have an expression such as this and we are requested to write this down as a single surd number. When is that possible? Well, in cases where you have multiple numbers and you would rather just present your number as a single surd number, you could be requested to write it back as a single surd number. So let's see how we can do that. So if we have an example 2 root 5 and we're requested to write this down as a single surd number. Now we know that this is equal to 2 multiplied by 5. Now our intention is to bring these two back into the radical sign, into the square root sign. Now if we have a sidebar here, if we have 2 and we're trying to express this under the radical sign, we know that the number we have to find the square root to get to 2 is 4. So 2 is equal to the square root of 4. So when you have a number you're trying to put under the radical sign, all you have to do is square it. So if you have a, this is equal to the square of a. And so that's what we'll do here. Now to make 2 go under the radical sign, we would have to square it and add the radical sign. So the square root of 4 results in 2 multiplied by the square root of 5. Now we can combine this because we remember the rule that says that the square root of a multiplied by the square root of b is the same as the square root of a, b. So if we apply that here, we can combine this into the square root of 4 multiplied by 5. And this is equal to the square root of 20. That is how you get a single surd. If we look at another example such as 8 root 2. Now this is the same as 8 multiplied by root 2. Now we want to bring 8 under the radical sign. So to do that, we have to square 8, which is 64, and then add the radical sign to it. So the square root of 64 is 8. We've not changed anything. This is multiplied by the square root of 2. Now we know that this is the same as saying the square root of 64 multiplied by 2. And this can be written as a single surd number as the square root of 128. That's our final answer. Let's look at a couple of more examples. If we are requested to write 5 root 3 as a single surd number. Now this is the same as 5 multiplied by root 3. Now if we're trying to bring 5 under the radical sign, we have to square it. So 5 times 5 is 25 multiplied by the root 3. And this is the same thing as 25 multiplied by 3, because we're combining these two, and 25 times 3 is equal to root 75. That's the final answer. If we look at 4 root 10, now this is the same as 4 multiplied by root 10. Now if we're trying to bring 4 under the radical sign, we square it. 4 squared is 16. We add our square root sign, multiplied by the square root of 10. And then we can combine these two as 16 multiplied by 10. And the final answer is the square root of 16 times 10, which is 160. And so if you're requested to write a split expression or a simplified surd as one single surd term, this is how we go about it. So from there, let's go into the multiplication. Let's go into the multiplication and division of surds. Now we already know that if you have the square root of a multiplied by the square root of b, this would result in the square root of ab. And we know that if you have the square root of a multiplied by the square root of a, we know that if you multiply the square root of a number by that number, it's one of the properties we've looked at, you would get that number. Now one that we've not seen is if you have a square root of b multiplied by c square root of d. Now we know that you can multiply the terms under the square root, so we know that this is equal to bd. We're just following the first row here. Square root of b multiplied by square root of d is equal to the square root of bd. But we can also multiply the terms in front here, which is ac. So ac. So if you have an expression where you have a number outside the radical sign plus the square root of a number b multiplied by a number c and the square root of d, you can have the answer by multiplying the numbers outside the radical sign and then combining the numbers inside the radical sign as well. So in this case, a root b multiplied by c root d is equal to a multiplied by c, which is what we have here, square root of b multiplied by d. So these and this forms this, and a combination of these and this forms this. So having said that, let's solve our first question. If we have 4 root 2 multiplied by 5 root 18, what is the solution to this? Now, as we've said before, we can combine the numbers outside the radical sign, which is 4 multiplied by 5. So this is 4 multiplied by 5. And then we can also combine the numbers under the radical sign, which is 2 multiplied by 18. And so this is equal to 4 multiplied by 5 is 20. 2 multiplied by 18 is 36. 20 root 36. But of course, we know that 36 is a perfect square. And so the root of 36, this is not a surd, we have to explicitly solve it. And the root of 36 is 6. So this is going to be equal to 20 multiplied by 6. And so our final answer is equal to 120. Now let's start with this one. And like we said, we can combine the numbers outside the radical sign. And so this is going to be equal to 2 multiplied by minus 5. And then we combine the numbers inside the radical sign, which is going to be equal to square root of 2 minus square root of multiplied by the square root of 7. So if we solve this, 2 multiplied by minus 5 is going to be equal to minus 10. And we can combine this to be the square root of 2 multiplied by the square root of 7. And so our final answer in this case is going to be minus 10 root 2 times 7 is 14. Now if we do the same thing here, we combine the numbers outside the radical sign for starters, so that's going to be minus 3 multiplied by 2. And then for the numbers inside the radical, under the radical sign, we have the root of 3 multiplied by the square root of 2. So this is going to be equal to minus 3 times 2 is equal to minus 6 multiplied by the square root of 3 times 2. And our final answer in this case is going to be minus 6 root 3 times 6. 3 times 2 is equal to 6. So minus 6 root 6 is our final answer. So first thing, combine the numbers outside the radical sign. So we have 2 here, multiplied by 3 here, multiplied by 5 here. And then we move on to the numbers under the radical sign, which is root 5 here, multiplied by root 2 here, multiplied by root 5 here. And so we can go ahead and say 2 times 3 is 6, 6 times 5 is 30. So all this becomes 30. And in this case, we can actually go ahead and do our straight multiplication, which is, if we solve it the first way, which is, we would say there's the square root of 5, which is this first 5, multiplied by 2, which is this, multiplied by 5, which is this. And that's 5 times 5, 5 times 2 is 10, 10 times 5 is 50. And so this is equal to the square root of 50. And then we'll later realize that we can actually break this down into 25 and 2. And because 25 is a perfect square, we know that if we bring this out, what we would have is the square root of 25 multiplied by the square root of 2, which is equal to 5 root 2. But we can as well have thought about that from here, because we know the rule that says that if you have the square root of a multiplied by the square root of a, this is equal to a. So from here, it means that if we have the square root of 5 multiplying the square root of 5 here, these two can combine to form 5. And then we'll bring the square root of 2 down here. And then our final answer is going to be 30 multiplied by 5, which is 150 multiplied by root 2. And that's the final answer for that multiplication. So let's move on to division of sorts. If we have an example, root 2 over root 8. Now remember the rule or the property of sorts that says that if you have root a over root b, this is the same as saying root a over b. We can go this way or this way, it doesn't matter. Now, it depends on the usage. Now this can be written as square root of 2 over 8, and this is equal to the square root of 1 over 4. Now, if we go back the other way, this is going to be root 1 over root 4. Because we know that root 1 is equal to 1. The square root of 1 is 1, doesn't matter. And we know that the square root of 4 is equal to 2. So ultimately, our final answer is that root 2 over root 8 is equal to 1 over 2. And if you solve this on your calculator, you actually find out that this is 0.5. And that's exactly what half is. Okay, if we solve another example, which is 4 root 12 over 2 root 2. Well, from here we can see that 2 cancels out 4, and so we can start cutting that down. We get our 2 here. 2 root 12 over root 2. And then we can rewrite this as 2 multiplied by 12 over 2, which is combining these two together using this property that we have here. And this is the same as 2 multiplied by root 6. And so our final answer is 2 root 6. We cannot break down root 6 any further than we have already here. So 2 root 6 is our final answer. If we have 5 root 8 over 10 root 2. Now 5 can already cancel 10 to give 2. So we have root 8 over 2 root 2. Now this can be written as 1 over 2. So we bring out the half. That's 1 over 2. And then we combine 8 over 2 as 8 square root of 8 over 2. Now this is 1 over 2. 8 over 2 is equal to 4. So the square root of 4. Now we know that the square root of 4, so let's bring our half here first. And we know that the square root of 4 is equal to 2. So 2 cancels out 2, and our final answer here is 1. The next thing we'll be talking about is the addition and the subtraction of surds. Now if we would recall how we do multiplications in normal algebra, if we have 3x multiplied by 2x, now what we do is multiply every term in this expression. So we multiply 3 by 2, which are the numbers 6, and we multiply the letters as well, which is x multiplied by x, which gives us x squared. If we also have 3x multiplied by 2y, now in this case what we have is 3 multiplied by 2, which is 6, and x multiplied by y, which gives us 6xy. And this is exactly what we do when we're multiplying surds as well. In a case where we have 3 root 2 multiplied by 4 root 2, we multiply the numbers outside of the radical sign, which is 3 multiplied by 4 gives us 12, and then root 2 multiplied by root 2 gives us 2. So this is ultimately. And in cases where we have different terms, such as 3 root 2 multiplied by 4 root 3, we multiply the terms outside, which is 12, and then we multiply the terms under the radical sign, which is 2 multiplied by 3. And this is the same as 12 root 6. But what if we have addition? What if we were to add up these terms instead? So what we would have is 3x plus 2x. And we will notice that we do this differently. What we do is we see this as 3x's and we're adding that to 2x's. So we don't multiply the terms, instead we add them up. So in this case, this is going to be 3x's, x plus 2x's, and this is going to give us 5x. And if we have 3x plus 2y's, well, this is not combinable, so we'll leave them like this. And that's exactly what we do when we're adding surds as well. In this case, if we have 3 root 2 plus 4 root 2, what we have is 3 root 2's, so we have 3 times root 2's, and we have 4 root 2's. And in this case, they become 7 root 2's. And when we have 3 root 2 plus 4 root 3's, here we can see that the terms are not the same. And so in this case, this is how we leave them. We have to find surds that are the same, like term surds, before we can add them up. The first example we'll be looking at says that we should find the square root of 3 minus the square root of 12. Now, as these are, we cannot do any combination here. Square root of 3 is a surd on its own. It can be left alone this way. Square root of 12 is a surd on its own as well. But we can break down 12. We can simplify 12. And we can simplify 12 by, we can then rewrite this expression as the square root of 3 minus, we know that square root of 12 can be written as the square root of 4 multiplied by 3. So if that's the case, it means that we can rewrite this as the square root of 3 minus the square root of 4 multiplied by the square root of 3. So this becomes this, just so that we're following. And this can be written as the square root of 3 minus The square root of 4 is 2 multiplied by square root of 3. So in this case, our surds are now the same, square root of 3 here and the square root of 3 here. And now we can see this as saying that 1 square root of 3 minus 2 square root of 3s, and that is going to be equal to minus 1 square root of 3. And so that's our final answer. So what we do is simplify where possible, collect like times together, and then carry out the subtraction or the addition. So in this case, there's nothing that can be further simplified. We can't simplify 5 or 3 or root 3 or root 2. So all we have to do now is collect like terms together. So if we start by collecting the root 2's together, so we have 3 root 2 here. We have another root 2 here, which is minus 2 root 2. Then we collect root 3's together, so plus root 3. And there's another root 3 here, so plus 3 root 3. And then finally we have our root 5, 2 root 5. Now we can add up. So 3 root 3 minus 2 root 2's. So 3 root 2's, we're taking out 2 root 2's from there. So that's all we have to do is just subtract the numbers outside the radical sign. And in this case, 3 minus 2 is going to be equal to 1 root 2. Now, root 3 plus 3 root 3's, that's equal to 4 root 3. And there's nothing to combine with root 5. So the final answer is root 2 plus 4 root 3 plus 2 root 5. And I hope that that's clear. Is root 3 plus root 48. Now obviously root 3 cannot be broken down, so that's that. But we can break root 48 down. And we can break this down by, remember how we learned how to simplify expressions. So we can simplify this by 16 multiplied by 3. And this can be rewritten as root 3, which is this one. And we know that if we find the square root of 16, that's 4. So this becomes 4 root 3. And so the final answer here is root 3. 1 root 3 plus 4 root 3 is equal to 5 root 3's. Final answer. Now obviously these are not like terms, so we can't combine them. So how can we do that? We have to simplify both terms. And so to simplify this, we have 3. 54 can be broken down as 9 multiplied by 6. And we know that 24 can be broken down as 4 multiplied by 6. Remember how we learned how to simplify. Write down the factors of this. Look for the highest perfect square we have. In this case is 9. And then we have to multiply 6 by 9 to get 54. That's how we came about this expression. And for 24, the highest perfect square we have is 4. And we have to multiply 6 by 4 to get 24. So if we further solve this, we have that 3 multiplied by the square root of 9 multiplied by the square root of 6 plus 2 multiplied by the square root of 4 multiplied by the square root of 6. And so this becomes 3 multiplied by 3, square root of 9 is 3, multiplied by the square root of 6, plus 2, multiplied by the square root of 4 is 2, multiplied by the square root of 6. So if we combine this, finally we can get that 3 times 3 is 9 root 6, 9 root 6, plus 4, 2 times 2 is 4 root 6. Now these are like times, root 6 and root 6, and we can combine them. So 9 root 6 plus 4 root 6 is 9 plus 4, and that would yield 13 root 6. So if we have the square root of 48 minus 3 root 72 minus root 27 plus 5 root 18. Now none of these are likes. So we have to find a way to combine them by simplifying them into like terms. So if we're breaking down for the 8, we know that since this is a lot, let me do them in different inks. So if we have this in black ink, we have that 48 can be broken down into 16 multiplied by 3 minus 3, which is what we have here, the root of 3. We can break down 72 into 36 multiplied by 2. Now we can break down 27 into 9 times 3. And we can break down 18 into 9 times 2. So these is equal to the square root of 16 multiplied by the square root of 3 minus 3 multiplied by the square root of 36 multiplied by the square root of 2. We're breaking down the expressions in the radical under the radical sign. So this is going to be equal to the square root of 9 multiplied by the square root of 3 and plus 5 here multiplied by the square root of 9 multiplied by the square root of 2. So the square root of 4 multiplied by 3 here is going to be square root of 16, is 4 root 3. The square root of 36 is 6. 6 multiplied by 3 is 18. So this is going to be minus 18 root 2. Square root of 36 is 6. 3 multiplied by 36 is what gives us 18. So 18 root 2. Minus the square root of 9 is 3. 3 root 3 is what we have here. And the square root of 9 is 3. 5 here multiplied by 3 is 15. So we have 15 root 2. So now we can gather like terms together and then carry out our additions and subtractions. So this is going to be equal to 4 root 3. Okay, we have another root 3 here, which is going to be minus 3 root 3. And then we have root 2, which is minus 18 root 2 plus 15 root 2. So our answer, if we combine this, 4 root 3s minus 3 root 3s is going to be 1 root 3 left. And then minus 18 root 2s plus 15 root 2s, minus 18 plus 15, and that's going to be minus 3 root 2. So our final answer is square root of 3 minus 3 square root of 2. Now we move on to expanding brackets, which is an extension of the multiplication of sorts that we've seen before. The very first form of expansion we'll be doing takes the form A into C plus D. Now if we have one term on the outside of the bracket which multiplies a number of expressions inside our bracket, all we have to do is distribute that lone expression over both terms in the bracket. And this is what I mean by that. We would have to multiply this by this expression first and then multiply it by the second expression as well. And so this is going to be equal to A multiplied by C plus A multiplied by D. So let's solve some examples, and don't forget all the previous rules that we've seen when doing multiplication in sorts apply as well. So the first example is going to be root 2 into root 5 plus root 3. Now don't forget, we're supposed to multiply root 2 by root 5 and then multiply root 2 by root 3 as well. So this is going to be equal to root 2 multiplied by root 5, which is the first part here, plus root 2 multiplied by root 3, which is the second part here. And so this is going to be equal to, we know we can combine these two into being root 2 multiplied by 5 plus root 2 multiplied by 3. And so ultimately this becomes root 10 plus root 6. And this is the final answer, as we can no longer go forward from here. The next example is root 3 into 2 root 2 minus root 5. Now don't forget, we multiply the first time, the outside term by the first term, and then multiply it by the second term as well. And so this is going to become, the first one is root 3 multiplied by 2 root 3. So this is going to be root 3 multiplied by 2 root 2. And this is going to be root 3 minus, obviously, minus root 3 multiplied by root 5, which is root 3 multiplied by root 5. So this is going to be equal to, remember when we're multiplying radical terms, we multiply the outside values and then also combine the values under the radical sign. In this case, this is just 2 multiplied by 1, so there's just 2 here. And then we can combine the terms under the radical sign by 3 multiplied by 2. And in this case, this is simply 3 multiplied by 5. And so this is going to be eventually 3 multiplied by 2 is 6 minus root 15. And that's our final answer. So let's do one more. If we have minus 7 root 5 into minus 3 root 20 plus 2 root 3. Now we do the same thing like we did for the previous two examples. And so we multiply this by this, and that gives us minus 7 root 5 multiplied by minus 3 root 20 plus minus 7 root 5 multiplied by 2 root 3. So this is going to be equal to, we multiply the outside terms, minus 7 multiplied by minus 3. That's going to result in 21. Remember that minus multiplied by minus is equal to plus. Minus multiplied by plus is equal to minus. Minus plus multiplied by minus is equal to minus. And plus multiplied by plus is equal to plus. So when you multiply the same signs, you get a positive sign. And when you multiply different signs, minus times plus or plus times minus will give you a negative sign. So minus 7 multiplied by minus 3 here becomes plus 21. And 5 multiplied by 20 becomes 100. So we do the same thing here. This is going to be minus 7 multiplied by 2. That's going to be minus 14. Remember, minus times plus. That's what we have here. Minus times plus is equal to minus. So that's minus 14. And then root 5 multiplied by 3. That's going to be equal to 15. So we know that we have to also combine these two signs, which is plus times minus. And this is going to be 21 root 100 minus 14 root 15. That's plus times minus. That's how we get this minus. I hope that's clear. So this becomes, we know that 100 is a perfect square, and that's the square root of 100 is 10. So this becomes 21 multiplied by 10 minus 14 root 15. And this is going to be equal to 21 multiplied by 10 is 210 minus 14 root 15. And we can go no further as there's no way to combine this. So what we just looked at is the form where there's one expression or one quantity outside of the bracket. What if we have an expression in the form a plus b multiplied by c plus d? Now what we have to do here is we take the first term here and multiply it by both terms in the second bracket, and we do the same for b as well. So we take b and also multiply it by both terms in the second bracket. And so what we would get is a multiplied by c, which is ac, plus a multiplied by d, ad, plus b multiplied by c, plus b multiplied by d, which is bd. And so if we take our first example under this, we'll have root 2 plus 3 multiplied by root 5 plus 3 root 3. Now don't forget, the first thing we have to do, let me add a little space here so I can. So don't forget, the first thing we have to do is multiply this by the first term here, multiply this first term by the second term in the second bracket, and then we multiply the second term in the first bracket by both terms in the second bracket as well. And so we have root 2 multiplied by root 5 plus root 2 multiplied by 3 root 3 then we move to the second term, which is 3 multiplied by root 5 and then 3 multiplied by 3 root 3. To make that clearer, we can separate each of those terms. This is easily combined as the square root of 2 multiplied by 5 plus, here the outside terms multiplied to give 3, which is 3 multiplied by the imaginary one we have here, so that's 3. And then the terms under the radical sign gives 2 multiplied by 3 plus 3, this is easily 3 root 5 plus the outside terms multiplied to give 9, 3 times 3, and there's only one term under the radical sign here, which is root 3. And so we can write this finally to be root 10, 2 times 5, plus 3 root 6, plus 3 root 5, plus 9 root 3. If we look through, there are no terms that we can combine here, so this is our final answer. The next example is 3 root 10 minus 2 root 5 multiplied by 4 root 2 plus 6 root 6. Now don't forget, this multiplied by this, and then this multiplied by this, and we also do this. Okay, so let's go. So that's 3 root 10. So 3 root 10 multiplied by 4 root 2, and then 3 root 10 plus 3 root 10 multiplied by 6 root 6, and then this is minus 2 root 5 multiplied by 4 root 2. So we're going to have a minus here because minus times plus is minus. So minus 2 root 5 multiplied by 4 root 2. And minus times plus is also going to give us minus. So that's minus 2 root 5. Let me write that clearly. That will be minus 2 root 5 multiplied by 6 root 6. Okay, so this is going to be equal to multiplying the numbers outside the radical sign. 3 multiplied by 4 is equal to 12. And then the numbers under the radical sign, that's 10 multiplied by 2. This becomes 20. Plus 3 multiplied by 6 is 18. And then 10 multiplied by 6, that's 60. Minus 2 multiplied by 4 is 8. And then 5 multiplied by 2 is 10. Minus 2 multiplied by 6 is 12. And 5 multiplied by 6 is 30. So this can be our final answer, because if we look at these two, we can actually break them down further. And so we can do this by expanding this to 4 multiplied by 5, which is 20 becomes 4 multiplied by 5. And 18, 60 becomes 4 multiplied by 15. Minus 8 root 10. Minus 12 root 30. So this becomes 12 multiplied by, we can break this up to be square root of 4 multiplied by square root of 5 plus 18. We can do the same here, square root of 4 multiplied by the square root of 15 minus 8 root 10 minus 12 root 30. Now this is going to be equal to 12 multiplied by square root of 4 is 2 minus the square root of 5 plus 18 multiplied by 2 multiplied by square root of 15 minus 8 root 10 minus 12 root 30. Now our final answer will be 12 multiplied by 2 is 24 root 5 plus 18 multiplied by 2 is 36 root 15 minus 8 root 10 minus 12 root 30. And that is our final answer. The next example says the square root of 2 plus 9 root 3 all multiplied by the square root of 2 minus 9 root 3. And so if we do like we've done before, we'll have that root 2 multiplied by root 2 plus root 2 multiplied by minus 9 root 3. And so that will make this a minus, because plus multiplied by minus gives us minus root 2 multiplied by 9 root 3 plus 9 root 3 multiplied by root 2 minus 9 root 3 multiplied by 9 root 3. So we have all our expressions taken care of. Now this becomes root 2 minus root 2 is going to be equal to 2. And we remember that from root a multiplied by root a becomes a. Remember this law. So root 2 multiplied by root 2 becomes 2 minus root 2 multiplied by 9 root 3 becomes 9, which is the numbers outside, which is 9 multiplied by 1 here. And then the numbers under the bracket, 2 multiplied by 3 becomes 6. And this 9 becomes 9 root 3 multiplied by 2 as well is 6. Minus 9 times 9 is 81. And root 3 multiplied by root 3 is 3. So finally we have 2 minus 9 root 6 plus 9 root 6 minus 243. But we see that minus 9 root 6 plus 9 root 6 will cancel each other out. It's like saying minus x plus x. It's going to be 0. So this is going to be 2 minus 243. And so our final answer is minus 241. So we're asked to evaluate a and b if 2 root 2 minus root 5 multiplied by root 2 minus 3 root 5 is equal to a plus b root 10. So we're supposed to write this, solve this expression until we get an expression that is similar to this, and then we can evaluate a and b. So if we expand this expression, we have that 2 root 2 multiplied by root 2 minus 2 root 2 multiplied by 3 root 5 minus root 5 multiplied by root 2 minus times minus is equal to plus this time around. So plus root 5 multiplied by 3 root 5. Okay, 2 multiplied by 1 equals 2. And we know that root 2 multiplied by root 2 is equal to 2 as well. So 2 multiplied by 2, we can easily write that down as 4 here. And root 2 multiplied by root 2 is equal to 2 as well. So this is what becomes 4. Now, 2 multiplied by 3 is equal to 6. And under the bracket, we have that 2 multiplied by 5, which is equal to 10. Minus root 2 multiplied by root 5 is equal to root 10. Plus 3 multiplied by 1, which is 3. And we know that root 5 multiplied by root 5 is 5. So we can also say that 3 multiplied by 5 is equal to, we can replace that by 15 here. So if we group like terms, we have that 4 plus 15 minus 6 root 10 minus root 10. 4 plus 15 is equal to 16. Minus 6 root 10 minus root 10 is equal to minus 7 root 10. And so this is our final answer. So if this is our answer, and we know that this is given in the form a plus b root 10, and you can definitely see that from here, a is equal to 16 and b is equal to minus 7. Minus 7. And that's how we solve that. The next thing we'll be looking at is rationalizing denominators. Consider an expression root 5 over 3. Mathematically, there is nothing wrong with this expression. It is correct and it is acceptable. However, if we exchange the numerator for the denominator here and we write this as 3 root 5, this is also a correct mathematical expression, but it is undesirable. And the reason why we do not desire our denominators to be radical expression is because if we have an expression such as this, it is easy for us to evaluate the value of this expression, because whatever the value of the numerator is, all we have to do is divide it by 3 and we get the value of this fraction. But in a situation such as this, whatever the value of the numerator is, it will be very difficult to divide that expression by a radical number root 5. So we will never get a true value of this fraction. Our aim when we have an expression such as this is to get rid of the radical sign here. And that is exactly what we mean by rationalizing the denominators. When we have an expression such as this, we get rid of the radical sign. So if we do that, how do we do that? If we have the expression 3 over root 5, now you would agree that if I multiply this by 1, it changes nothing. I have 3 root 5 as well. But how does this help me in rationalizing this fraction? Now what I need to do is find a way to multiply this by 1, but get rid of the radical sign in the denominator as well. Now, consider this. If I have 3 root 5 multiplied by root 5 over root 5. Now you would agree that root 5 over root 5 is equal to 1, which is essentially the same as what we've done here. The difference is that we're expressing our 1 in a different way. So if we work this out, you would notice that 3 multiplied by root 5 will become 3 root 5. And root 5 multiplied by root 5 will become 5. And so this has helped us gotten rid of the radical sign in the denominator, and we've rationalized this fraction. The value of this expression is exactly the same as the value of what we started from. The difference is that we've been able to get rid of the radical sign in the denominator. And that's exactly how we rationalize surds. So if you have an expression a over root b, all we have to do is multiply the numerator and the denominator by the denominator here, and we'll have our expression in the form a root b over b. Let's solve some examples so that we are sure. If we are requested to rationalize the fraction 1 root 7, so don't forget, all we have to do is multiply by root 7 for both numbers, and here we'll have root 7 over 7, and that's our final answer. What about 20 root 5? Simple. We multiply both numerator and denominator by root 5, and so this is going to be equal to 20 root 5 over 5. Rationalized. What if you have 2 root 3 over root 5? We do the same thing, multiply numerator and denominator by the denominator here, root 5, and this is going to be equal to 3 multiplied by 5, which is 3 multiplied by 5 over 5, and our final answer is 2 root 15 over 5. What if we have 6 root 7 over 5 root 2? In this case, we multiply the numerator and denominator only by the radical portion of this expression. We don't need to multiply by 5 root 2, only by root 2. So we multiply both sides by root 2, and this becomes 6 root 7 multiplied by 2, 14, and 5 multiplied by 2 root 2 is equal to 2. And so this is going to be 6 root 14 over 10. And we can cancel, 2 can cancel both of these out to give 3 root 14 over 5. So what if we have root 5 plus 2 root 2 over root 5? We multiply the top and the bottom by root 5. This is going to be equal to root 5 multiplied by 5 is equal to 5, plus 2 root 2 multiplied by root 5 is equal to 2 root 10. Now root 5 multiplied by root 5 is equal to 5. What if we have an expression that has more than one term, such as root 3 over root 2 minus 7? Now recall that this is not a multiplication, so we cannot just take out the radical portion of this expression. Now the first instinct is to multiply this by root 2 minus 7 multiplied by over root 2 minus 7. But let's see how this works out. So this becomes root 3 multiplied by root 2. That becomes root 6. And then root 3 multiplied by minus 7 becomes minus 7 root 3 over root 2 multiplied by root 2 is 2. Root 2 multiplied by minus 7 is minus 7 root 2. Minus 7 multiplied by root 2 becomes minus 7 root 2. And minus 7 multiplied by minus 7 becomes plus 49. And so this would eventually becomes root 6 minus 7 root 3 over 2 plus 49, that's 51. Minus 7 root 2 minus 7 root 2 becomes minus 14 root 2. But we have failed to get rid of the radical sign in the denominator. But see, if we try this out, see what happens. If we do this, which is root 3 over root 2 minus 7 multiplied by root 2 plus 7 over root 2 plus 7. If we solve this, we would have that root 3 multiplied by root 2 is equal to root 6 plus 7 root 3, which is root 3 multiplied by plus 7. Now the denominator, root 2 multiplied by root 2 becomes 2. Root 2 multiplied by plus 7 is equal to plus 7 root 2. Minus 7 multiplied by root 2 becomes minus 7 root 2. And minus 7 multiplied by 7 becomes minus 49. Now if we solve this is going to be equal to root 6 plus 7 root 3. 2 minus 49 becomes minus 47. And we can see that plus 7 root 2 minus 7 root 2 can cancel out each other. And this is a rationalized fraction. And so we can see that a more correct way of expressing this would be minus root 6 plus 7 root 3 over 47. And we have our rationalized surd. So when we have an expression such as x plus y or x minus y as the denominator which we are trying to rationalize, what we do is multiply the denominator and the numerator by the conjugate of that denominator. Now what do I mean by conjugate? If we have an expression root a plus root b, the conjugate of this expression is equal to root a minus root b. If the expression is c minus root d, the conjugate of this expression is c plus root d. All we have to do is change the sign in the denominator, and that gives us the conjugate, and that's what we multiply the numerator and the denominator by to rationalize that expression. So if we do another example, if we have the expression root 2 plus 5 over root 3 minus root 2. Now the denominator we're trying to rationalize is this, root 3 minus root 2. The conjugate of this is going to be equal to root 3 plus root 2. The same numbers, we only change the sign here. So this is going to be multiplied by root 3 plus root 2 over root 3 plus root 2. And if we solve this, we'll have that root 2 multiplied by root 3. And now don't forget, this is the same as saying as the expansion that we just learnt, which is you're basically trying to expand or multiply two expressions. It's the same rules as the expansion that we just learnt, which is multiplying this by this and this. So this becomes root 2 multiplied by root 3, which is going to be equal to root 6. And then root 2 multiplied by root 2, which is going to be equal to plus 2. 5 multiplied by root 3 is going to be equal to plus 5 root 3. And 5 multiplied by root 2 is going to be equal to plus 5 root 2. The denominator in this case is going to be root 3 multiplied by root 3, which is going to be equal to 3. Root 3 multiplied by root 2 is going to be equal to plus root 6. Minus root 2 multiplied by root 3 is going to be equal to minus root 6. And minus root 2 multiplied by root 2 is going to be equal to minus 2. So these can cancel out this, and we can write our final expression as root 6 plus 2 plus 5 root 3 plus 5 root 2 all over 3 multiplied by 2 is 3 minus 2 is 1, and we don't need that actually, so our final expression is actually this. If we have another example, 2 root 3 over root 5 plus 2 root 6. Now to rationalize this, we multiply both the numerator and the denominator by the conjugate of this denominator, which is going to be root 5 minus 2 root 6 over root 5 minus 2 root 6. So 2 root 3 multiplied by 5 is equal to 2 root 15 minus 2 root 3 multiplied by 2 root 6. We multiply the outside term. 2 multiplied by 2 is 4. And then the terms under the radical sign, 6 multiplied by 3 is equal to root 18. For the denominator, root 5 multiplied by root 5 is equal to 5. Root 5 multiplied by minus 2 root 6 is equal to minus 2. 6 root 6 multiplied by 5 is 30. Root 2 root 6 multiplied by root 5 is equal to plus 2 root 30. And 2 root 6 multiplied by minus 2 root 6 is equal to minus 4 root 36. Now this becomes root 2, excuse me, 2 root 15 minus 4 root 18 over, now this cancels out this to give us 5 minus 4 root 36. We can further write this as 2 root 15. We can reduce this from here. We can see that this is equal to 9 multiplied by 2. And we know what that means. We have to take 9 out of this because this is a perfect square. And also, if you look at this, 36 is a perfect square as well, which means that this is going to be 4 multiplied by 6. So this is going to be 2 root 15 minus, if we bring 9 out of the radical sign, it becomes 3. 3 multiplied by 4 is 12. So 12 root 2 over 5 minus 24. 5 minus 24 is equal to minus 21. And our final expression is minus 2 root 15 minus 12 root 2 over 21. That's our final answer. The next question says, evaluate A and B if 3 root 3 over root 3 minus root 2 is equal to A plus root B. So let's bring this expression out and rationalize it and see if we can get an expression of the form A plus root B. So if we do that, we have that 3 root 3 over root 3 minus 2. Now to rationalize this, we multiply the numerator and the denominator by the conjugate of the denominator here, which is root 3 plus root 2 over root 3 plus root 2. Now this is equal to 3 root 3 multiplied by root 3. This is 3 here, which is the 3 multiplied by the imaginary 1, and root 3 multiplied by root 3 becomes 3. So this is 9. So this becomes 9. And 3 root 3 multiplied by root 2 becomes 3 root 6. For the denominator, root 3 multiplied by root 3 becomes 3. Root 3 multiplied by root 2 is plus root 6. Minus root 2 multiplied by root 3 becomes minus root 6. And minus root 2 multiplied by plus root 2 becomes minus 2. And then we can see here that root 6 can cancel out root 6 because plus root 6 minus root 6 is equal to 0. So we can write this expression as 9 plus 3 root 6 over 3 minus 2 is equal to 1. So this is equal to 9 plus 3 root 6. But this is not exactly in the form we were given in the first place, because we can see that this is definitely not this. So what we're required to do is to express this term as a single surd term under the radical sign. And I hope you remember how to do that, because all we have to do is take out this term, which is 3 multiplied by root 6. And to bring 3 under the radical sign, we have to square it and then add a radical sign, multiply by this, and this becomes root 9 multiplied by 6, which is equal to root 54. So if we put this back into this expression, we have that this becomes 9 plus root 54. And if this is equal to a plus root b, then we can tell that a is equal to 9 and b is equal to 54. And that's all about surds. We've been able to see how to simplify surds, how to write surds in the single surd expressions, the addition, multiplication, division, and subtraction of surds. We've also been able to see expanding brackets in surds and rationalization of surds. I hope you've been able to understand everything we've taught in this video. See you in the next one. Thank you very much.